Okay, so we're going to balance some redox equations now. I've got a couple different ones. We're going to balance them in what we're going to call acidic versus basic solution, and we're just going to work through all the different steps and nuances that go into this process. First thing is everything that we've learned before, this idea that you need to be able to figure out what's oxidized and what's reduced, what's the oxidizing and reducing agent, all that stuff is going to come back. It's going to stick with us. In fact, I'm going to talk about it in this video as if you already know how to do that. So if you're unfamiliar, go back and make sure you have those other tools mastered. Definitely things that you would cover in the first semester of a general chemistry class, wherever you would be. Okay, so first thing that I'm going to do is go through and assign an oxidation number to every element that's in this equation. So iron plus 2, oxidation number is plus 2. Oxygen's a minus 2. Manganese then, because there are 4 oxygen atoms, manganese has to be a plus 7. Iron here is going to be a plus 3. Monatomic ions are great. Manganese plus 2 is going to be a plus 2. And now at this point, you really don't need to pick out, okay, what's oxidized and what's reduced. We're going to do that sort of as we work through the problem. So what I'm going to do first is I'm going to go through and break this reaction up into half reactions. So I'm going to look at, okay, I've got iron here that's a plus 2 and iron here that's a plus 3 oxidation number. So I know that that's a change in oxidation number. So I'm just going to write down iron plus 2 to iron plus 3. And then I'm going to say, okay, oxygen, all right, it's on the left but not on the right. That's the weird thing about redox. Balancing redox is that sometimes you won't have elements on both sides, and then it's like, what do I do? We'll see how to handle that. So we can't do anything with oxygen. It must not be oxidized or reduced here. But manganese is plus 7, and here it's plus 2, so it changes. So we have permanganate ion, 2 Mn plus 2. And now what I'm going to do is I'm going to decide whether those are oxidation or reduction. So plus 2 to plus 3 means the oxidation number is increasing. So that is an oxidation process. And in this case, the oxidation number is going from a plus 2 to a plus 3. That's a difference of 1. That difference in oxidation number is the number of electrons that's transferred in that half reaction. So in this case, there's 1 electron transferred. Now we have permanganate to Mn plus 2 ion, plus 7 to a plus 2. Oxidation number getting smaller, that's a reduction. Plus 7 to plus 2. The difference in oxidation numbers corresponds to the number of electrons, and that's 5 electrons. Okay. Next step, moving downward, we're going to go through and we're going to add the electrons in and then make sure everything is balanced. All right. Probably a good step at this point even to make sure things are balanced. So 1 iron here and 1 iron there, balanced. 1 manganese here, 1 manganese there, balanced. All right. So I'm going to do, if I have an oxidation, it means the electron's being given away. So the electron is a product. Fe plus 2 produces Fe plus 3 plus the 1 electron that we determined earlier. Now permanganate is being reduced. That means that species is gaining electrons. So in that case, the electrons would be a reactant. So we have 5 electrons plus permanganate ion to manganese plus 2 ion. Now at this point we're going to go through and we're going to balance everything else. And what I mean by everything else is there are 4 oxygen atoms here and we have none on the right hand side. So if we want to get some oxygen atoms on the right hand side, what we're going to do is we're going to add There are 4 oxygens here. We need 4 oxygens there, so we're going to add 4 water molecules. Why 4 water molecules? Because now that 4 gives us 4 oxygens on the right-hand side. Now you can probably see what the problem is, right? Because now I've introduced this new element of hydrogen on the right, but I don't have any hydrogen on the left. So I've added 8 hydrogens to the right. I've got to have 8 hydrogens on the left. In what form do we have them? As protons, H+. So now, the exciting thing is, if I were asking you, okay, what are the 2 half reactions? You'd be done, okay? So you'd be completely finished. But we're not. We want to balance or get the balanced redox reaction. So the third step is going to be to take these 2 half reactions and we're going to make sure that they have the same number of electrons. So this half reaction has 5 electrons in it. This one has 1. So I need to take this one and I need to end up with 5 electrons in this one. To do that, I'm just going to multiply everything in that equation by 5. So I'm going to get 5 Fe plus 2, 5 Fe plus 3, and 5 electrons. It'll be obvious here in a second why we have to get the right number of, or the same number of electrons in both. The other reaction, in this case, we don't have to do anything to. So 8H plus 5 electrons plus permanganate, manganese plus 2 plus 4 water molecules. Now that I've balanced both, all the elements in both are balanced, they both have the same number of electrons, we can add them together. And when we add reactions together, everything on the left-hand side of the arrow stays on the left-hand side. So 5 Fe plus 2 plus 8 H plus 5 electrons plus permanganate ion. And on the right, I have 5 Fe plus 3 plus 5 electrons plus manganese plus 2 plus 4 water molecules. Anything the same on both sides of those of that reaction? Same in the reactants and the products? Yeah, you should notice same number of electrons they cross out. That's why you got to get the same number. All right, we want those electrons to cross out. We don't want them part of that final reaction. We're sort of hiding the fact that the electrons are being transferred. And nothing else, so we can just write 5 Fe plus 2 plus 8 protons plus permanganate ion to produce 5 Fe plus 3 plus Mn plus 2 plus 4 water molecules, and done. Okay, now, the one thing about this, though, when we look at this reaction, do we notice anything about like pH or acidity or anything that's there? Anything that might strike you about that? That H+. Remember H+ we said was sort of the definition of acidity? And, so because we have H+ hanging around, we call this balanced in acidic solution. All right? So whenever you're asked to balance a redox equation, oftentimes you'll be told, okay, that you should balance this in acidic or in basic solution. Some of them, it's not going to matter. The one we did in class didn't matter at all because there was no H+ or OH- or anything hanging out. We didn't have to do anything with it. But this is in acidic solution. Now, my question, or the next question that we're going to look at is, all right, so now that we have this expression, what if we don't want it in acidic solution? What if we want to know how to balance this in basic solution? So what we're going to do is we're going to go through and we're going to transform this acidic solution expression to one where there's basic solution. And we know already, all right, that if we react H+ with OH-, we end up with water. So if we want to neutralize the H plus and get this to basic solution, we could take and we could add 8 hydroxide ions to that side that has the H plus, in this case, the reactant side. And those H plus and those OH minus would react together to produce 8 water molecules. Now, we know if we add something to the left-hand side of a chemical reaction, we have to add it to the right-hand side too. Same as if we were working with a mathematical expression. So we can't just add the 8OH to the left, we've got to add it to the right-hand side too. Now we're going to go ahead and add those two things together. So we get 5Fe plus 2. If you feel like you're writing the same thing over and over again, well, indeed, that's what you do. But now we don't write H plus and OH minus. Those two things combine in order to produce water. So we get 8 water molecules. On the right-hand side, just writing everything, 5Fe plus 3, Mn plus 2, 4 water molecules, but now we have those additional 8 hydroxide ions. Okay, so notice we've gotten rid of the H plus and we have OH minus, but we're not done. Okay, you might say, oh, but that's basic solution, Dr. Ramsey, and indeed you would be right about that. But what is it that we have to take care of first? Yeah, those water molecules, right? Okay, so we have the water molecules on both sides. So we got to get rid of them from one of the sides. So what we're going to do is we're going to take 4 away from the right-hand side, and we're going to take 4 away from the left-hand side. Now we can just rewrite it. So 5Fe plus 2 plus permanganate ion plus 4 water molecules to produce 5Fe plus 3 plus Mn plus 2 plus 8 hydroxide ions. Now we are done. Now, basic solution. Why basic? Because we have the 8 hydroxide ions there. Okay, so that's probably the middle of the road when it comes to balancing a redox reaction. All right, not the most difficult one, but not the easiest one like we saw in class. In class, that was probably the easiest case, or in our lecture, our last lecture, set of lecture notes. So this is probably the intermediate one. There's also going to be another video where I'm going to do one that's a little more complicated. It's actually going to be not going to be exactly the same, except there's going to be one step at the beginning that we have to watch out for, and I will tell you, students always mess this part up. Okay, so it's important that you watch that next video. Even if you're like, oh my gosh, yeah, I got this, I can do it, no sweat, watch the next one, okay? Even if you just get through the first step and then you pause it and then you work the rest on your own and you check it, that is fine. But watch like the first, couple minutes of it just to make sure that you get everything right. Okay, all right, catch you in the next video.